So some definitions of scale, and there are many of these things. There are four main ones, I think. Cartographic scale is the ratio between the distance on a map or an image to its corresponding distance in the real world. And I won't be talking about that in this presentation. Geographic scale I define as the spatial extent of a research area. Observation, or sometimes called measurement scale, is the magnitude of the units for which data are analysed, and that obviously links to what people have been referring to as the MORP, the modifiable area unit problem. And then the last one is the operational scale, the dimension over which certain processes operate. And I'm going to call that process scale. So that's what I'm going to be talking about primarily in this presentation. But it also links to, at the very end, I'll come back to how this links to observation scale and the modifiable area unit problem, and also to the spatial extent of a research area and what influence that might have on our results. Okay, so what do we mean by process scale in geography, and what do I mean by it? Basically, it's the geographical scale, which extent or range might be words one would use, over which a particular process is relatively uniform. And we're all aware of this effect, and we use this term in many different contexts. So we talk about macro and microclimatic effects. We talk about urban heat islands, and we talk about global warming. Okay? They obviously, those are processes which operate at different scales. We talk about global, regional, and local factors affecting economics, local economies, unemployment rates. We talk about fishing stocks and a product of overfishing being a local overfishing, too many people fishing in a local area, but also global warming, global rise in sea temperatures. So we talk about this, and we actually appreciate that these things occur over different spatial scales. Implicitly, we are making that assumption. But how do we measure it? So the importance of this kind of process scale and the measurement of it, both of these things have long been recognized. And, Jingle mentioned going back to 1999, Harvey, right, was mentioning these things before his crisis of faith in 1967, right? So he said different processes become significant to our understanding of spatial patterns at different spatial scales. Geographers have been concerned with it for a long time, right? A long time. But he also said, we have no measure of the scale at which a particular process has most to contribute to the formation of a spatial pattern. Marceau, in a review in Remote Sensing, Canadian Journal Remote Sensing, said, 1999 again, an understanding of how processes operate at various spatial scales and how they can be linked across scales becomes a primary goal when investigating complex phenomena. And again, that was touched upon this morning by several people. The paper by David Manley, Flaudio, and Steele, 2006, echoed David Harvey's words. Spatial distributions are based on processes taking place in geographical space. A mapped pattern may reflect several distinct processes. So it's separating what we see, the visible up here, the pattern, from the invisible, the processes which have led to that pattern, each of which may affect a different area and operate at a different scale. The challenge for the spatial analyst is to identify these processes and evaluate their importance from the spatial pattern observed. Okay? So this is a kind of standard problem. And 50 years, at least now, after Harvey's lament about our inability to measure the scale at which different processes operate, we haven't found a solution until now. Okay, right. And like many of life's problems, we can find a solution in local modeling. So, and particularly this type of local modeling. So multi-scale geographic weighted regression. And the idea here is that we've basically got a model where the parameters of this model are allowed to vary over space, as in geographic weighted regression, but they're allowed to vary over space at different scales. So each of these covariates, the conditioned relationship, say, between x3 and y, is defined by a bandwidth, which is specific to that covariate. And each of these, however many covariates we have in our model, these are a conditioned process. How x1 conditioned on x2 and x3 affects y. And these conditioned processes might vary. Okay, they might be global. Who knows? So this one might be the same everywhere. This conditioned process of X3 on Y might be the same everywhere across our study area. We don't know that. It might well be. The conditioned process of the relationship between X2 and YI, conditioned on X3 and X1, might vary a little bit. It might vary regionally, smoothly over space. And finally, the conditioned relationship between X1 and Y might vary a lot. Okay? So multi-scale geographic weighted regression allows this possibility to happen, that processes might operate at different spatial scales. Now, just a quick sidebar on data versus processes, because again, this touches upon, I think, some of the discussion we had this morning. Basically, out there are spatial data which we can measure. And from these data, we can measure certain types of associations. It could be an auto dependency function, or it could be regression coefficients between attributes, or it could be correlations, etc. But we can measure these things. Okay, that's out there. From these associations, we must infer something about spatial processes, which we cannot see. But we know these spatial processes are the things which are determining the data that we measure. We just can't see them. So we have two realms, okay, and this is one way, and there are many ways, but it's one way of thinking about scale effects. So there are scale effects which are up here at the visible. So there are scale effects in dependency. We see it all the time in geostatistics, right? The range of a semi-variogram tells us what kind of structure there are in some measured data, right? Or the modifiable unit problem. Again, it's a measured effect of scale. But there are also invisible scale effects, these things that we cannot see, these processes which are affecting what we measure. And we don't know what's going on there. There might be different scale effects in different processes. So when we look at something like a semi-variogram, we're looking at the visible portion of the spectrum. Right? It's not telling us anything about the scale at which the processes which have produced our variable are operating. Right? It's essentially a descriptive statistic. So how can we use what is a bandwidth statistic in multi-scale GWR to indicate the scale of a process, which is invisible to us? Well, basically, the problem is, if we want to calibrate a model specific to each location, we don't have enough data to do that. Ideally, if we had 1,000 observations at each one of these locations, we wouldn't merge them together, right? We'd calibrate a separate model for each location, right? We do that for cities now. People run a model for Buffalo, New York, another one for Albuquerque, New Mexico, etc. You don't tend to merge those data. If you've got enough data at each location, why not just calibrate your model separately? So we'd want to do that. The problem is we don't have enough data typically to do that. So the solution is, let's just borrow some data from nearby locations. And we can do that at every location in space. We can just say, there's our focal point, and we can calibrate a model, it doesn't matter what kind of model it is, for that location by borrowing data from nearby locations. So in doing that, what we do is we give the data some weight between 0 and 1. And that weight is a function of how far away they are from the regression point. On the basis of close locations, which will have larger weights, closer to 1, the processes that we are trying to measure at that location are more likely to be similar from data which are nearby to that location. Distant locations, on the other hand, will be given a low weight because there the processes will be more dissimilar to the ones we are trying to estimate at the regression point. So the amount of this distance decay effect, how we transfer distance into weights, is controlled by what we call the bandwidth. But what is this bandwidth? What do we mean by that? Okay? Well, think about what happens if we make it too small or too large. So if we have too small a bandwidth, we make it very small. Right? The local parameter estimates will have low bias because we're just taking data from near the regression location, but they'll have a very high variance, a very high uncertainty, high standard errors, because there are very few data points on which the calibration is taking place. if you choose too large a bandwidth, the local parameter estimates will have low variance because you've got a lot of data to calibrate your local model with, but they'll have higher bias because we're taking data from further afield where the processes are more likely to be different. So this bandwidth is actually, when we optimize it in the calibration of the model, is a trade-off between bias and variance in our model. So if this were the ideal bandwidth, if we choose too large a bandwidth, we'll get low variance on our parameter estimates, but they'll have a higher bias. And if we choose a much smaller bandwidth than the optimal, then the parameter estimates will have a high variance, high amount of uncertainty, but they'll have low bias. So bandwidth selection is actually a trade-off between bias and variance. And we do this in our program by optimizing a goodness of fit statistic, which incorporates both bias and variance. And an Akaike information criterion does this. And in this case, for AIC, the smaller the value, the better. So typically what happens is, if we change the bandwidth from something very small to something very large, we get this characteristic shape. And what we want to find out is what distance is optimal in this, in terms of minimizing a combination of bias and variance. If it's too small, then we'll have parameter estimates which will, great, have low bias, but they'll have high variance. If we choose too large a bandwidth, we go up too far to get our data, the parameter estimates will have high bias, which is bad, but they'll have low variance, which is good. We want somewhere in the middle. And that's part of the routine. This is from a simulated data set to show you what happens. So on the left-hand side, that's the AIC plot here, as we change the bandwidth for a simulated data set. And you see this nice minimum value here. So that's our optimal bandwidth there. And here, it's the same, with the same data set, since we've simulated them, we can actually measure the amount of bias when we change the bandwidth, which is the blue line, and the amount of variance in the parameter estimates, which is the green line. And you can see that this is pretty much close to this kind of a nice optimal mix. It depends on your weight between bias and variance, obviously. But you can see what's happening with this AIC measure, that we're actually finding a bandwidth which gives us some kind of measure of a very low, relatively low bias and relatively low variance, which is what we want. So how is this, what's this got to do with scale? Well, the bandwidth, the optimal bandwidth, is an indicator of scale. Because my definition of it is the optimal bandwidth is the distance, or it could be the number of nearest neighbors, at which the addition of a further data to the local regressions increases the bias in the local parameter estimates more than it reduces the uncertainty in the estimate. So it's like a tipping point. So in essence, the bandwidth that we get in MGWR is the distance beyond which adding further data to the local calibration has an overall negative impact on the local parameter estimates. And it also indicates, and it kind of indicates, therefore, the scale over which a process operates. It's the equivalent to the range in a semi-variogram. Only this is for processes. It's a much deeper system. If a process were global, it's the same everywhere. Adding data to your local regressions will not increase bias, because the process is the same everywhere. But it will reduce the variance. So the optimal bandwidth will be very large. In a global model, the bandwidth is actually infinite. Everywhere gets a weight of 1. If a process is very local, however, it varies over space, then when you add data to the local regression, it will introduce increasing amounts of bias, right, which are not offset by the reduction in the parameter estimate variance. So the optimal bandwidth will be relatively small. So when we have local processes, the bandwidth, the optimal bandwidth in MGWR for that covariate will be small. If we've got kind of regional processes, and these aren't data, right, these are processes we're looking at here, then the bandwidth will be moderate. If we have a process which is global, it's the same everywhere, then the bandwidth will be very large. It'll tend to infinity. Okay. Let me just give you an example of that with something that is probably on our minds right now. Presidential elections. So these are data at county level from the 2016 presidential election. And it indicates the voter share in a straightforward fight between Republicans and Democrats for either party. The blue are counties where the majority of people voted for the Democrats, Hillary Clinton, and the reds are counties where the majority voted for Donald Trump. Yeah. So there's our kind of raw data, and we're interested in trying to understand excuse me, the voter pattern. And we've got 14 socioeconomic variables in here. All the usual suspects are in here. Age, gender, race, foreign-born, percentage of people with health insurance, since that was a big talking point in the 2016 election, income, education, a Gini coefficient measuring income inequality within each county, manufacturing employment, which is also a big talking point in the 2016 election, turnout, third-party votes, and population density, which separates urban and rural areas. All the variables are standardized. They've all got the same magnitude, a mean of 0, variance of 1. Calibrate a global linear model in usual form, and we see results like this. Okay, so in here, there are a number of variables which have a significant impact on voter preference across these counties. All the ones in blue have a positive association with Democratic vote. The negative one, income, has a negative association with the Democratic vote. Given all the variables are standardized, you can compare these parameter estimates and see which ones are most influential. African American, bachelor education, etc., income, Hispanic population have big impacts upon voter preferences, and these are the ones have less, slightly weaker impacts, but they're all significant at the 99% level. Okay, the problem, obviously, in doing that is when we look at the residual map, it looks like that. It's absolutely horrendous. The estimation's poor for some counties. Residuals as large as 50% in some cases. But they're also clustered, significantly so. The Moran's-I is 0.3. It's significantly different from 0. And obviously that makes inference a problem. And it also is a possible indication of spatially non-stationary relationships. That these determinants of voting behavior might vary over space. So a solution calibrated by MGWR, and the software is available, free software download from our website. Okay, when we do that, there's the original map of residuals, the problem case, and here's the residual map from MGWR. The R-squared has gone up to 0.95 from 0.66. Most of the residuals are around 0, and there's no spatial order correlation in them, no dependency. Yeah. Now, in the MGWR calibration, we get covariate-specific bandwidths for each of these covariates in our model. The number of counties used in this data set is 2850, so we can separate these roughly in order of magnitude in terms of how local a process is. So we've got processes at the top, the impact of the conditioned impact of manufacturing, for example, on voter preference, the conditioned impact of income on voter preference, those are global. They're the same everywhere across the country. These ones here in blue, cyan, they're varying across the country, but at a kind of regional scale. And then we go down to ones at the bottom here, are very local. The process here is very local. What it means is that that process is varying over short distances. Okay. So we can separate these things out into roughly global, regional, and local processes. Now, this morning, several people mentioned uncertainty. Okay, so there's obviously uncertainty in the bandwidth when we estimate this. There's noise in there. So we can incorporate that, and there's a paper coming out in the annals on this. So we can do, I'm not going to go into the technique, it's all in here, but we use Akaike weights to measure the uncertainty of these bandwidths. So not only can we estimate a bandwidth, an optimized bandwidth, but we also get confidence intervals for it. So we can use these to actually say one process is more local than another, right? And we can do that with a certain degree of confidence. And you can see the confidence intervals are actually quite narrow for these things. So if you're comparing them, you can make these statements that, yeah, these are regional and these are local. They're very different kinds of processes in terms of scale. So we have some relationships in this model, and these are parameter estimate maps. This is manufacturing, the conditioned impact of manufacturing on voter preference for the Democratic Party. This is conditioned impact of income on voter preference for the Democratic Party. They're all the local parameter estimates are pretty much the same everywhere across the country. These are the global relationships. Right? They're all significantly negative in both cases. Then we have a set of regional relationships where the parameter estimates, vary over space, but on a kind of broad regional level. So the left-hand side is the conditioned impact of Hispanic concentration in each county on how that county voted for the Democratic Party. Obviously, it's significantly positive across the country, but it's stronger across the Southwest. This is the impact of income diversity, the Gini coefficient, on voting for the Democratic Party. Most of the country, it's not significant, okay? But it identifies the Deep South very, very clearly, where you have voter registration laws, okay, that prohibit, well, that are not designed to, but have the effect of prohibiting lower income voters from voting, okay, which favors then the Republican Party. So you get a significant negative impact here, you get significant positive impact out west. The rest of the country, not an issue. And then you get local relationships. So here are two. This on the left is the impact, the conditioned impact of third-party votes on the vote for the Democratic candidate. And again, it's not uniform across the country. And why should it be? The third-party candidates were quite different. So out west, centered on Utah, the candidate was actually there's evidence here of vote transfers from the Democrats to the alternative Republican candidate, right, Evan McMullin, because there was a chance that he would actually win the state of Utah over Trump. So the Democrats are switching their votes. And so there you've got a significant negative impact on the Democratic vote of the third-party voting. Whereas, again, you see variations in the other part of the country, particularly the South, where a third-party candidate actually favored the Democrats. And then the last one, is just an example, is okay, frozen. So the last one, go on one more, is the impact of African American voters within each county. So again, it's significantly positive. Associates significantly positive. Remember, it's conditioned upon the other 13 variables in the model. It is significantly positive in almost all counties, apart from, right, Arizona, Colorado, Iowa, bits of Wisconsin, New England, southern tip of Texas, Oregon, and Washington. And obviously, what joins all these in is a very low concentration of African Americans, right? And so you're seeing again the impact, and the big gradations in here. You can't see it there, but there are darker blues and lighter blues in here. So the impact of the African American vote on African American voters, on the Democratic vote, varies quite substantially locally across the country. And then finally, the intercept picks up context. It picks up the impact of place on voter feeling. So this would be the situation if all the counties had exactly the same population mix. How would they vote? Well, you're picking up the Deep South voting Republican. You're picking up Florida, central and southern Florida being Democrat, northern Florida being Republican by heart, okay? And which is probably a fair representation of the state. And then you've got the blue wall of Democrats across the north and then down the west coast. So we're picking up this with the local intercept. And again, this is very local, a local process here of place on voting. So what we've gone from is OLS to GWR, which just had one bandwidth. It was an average across all covariates, to now MGWR, which allows processes to operate at different spatial scales. And that's the important thing for this meeting. We can do that. So just to summarize, right, we now have a method of measuring and comparing the spatial scale over which different processes operate. This has been a sort of holy grail almost, or since Harvey's words. We know that scale is important, and we suspect that processes might vary over space, but we don't know what scale that variation takes place. We now have a way of measuring that. Okay, it may be flawed in some aspects, but it's a way of getting at this issue. And what it is equivalent to the concept of range in a semi-variogram. But obviously, for the much more complex situation where we have a series of conditioned processes, we're not talking about data now, right? Data up here, processes are down here. We're trying to get at what these processes are and how or if they vary over space. And we're currently working on what features of a process, by that we mean degree of dependency. This is in the parameter estimates, or variation, magnitude, what kind of things determine the optimal bandwidth and hence scale? And then finally, if you think about the spatial non-stationarity of processes, it also provides an explanation. It might not be the explanation. It's an explanation for the impact of geographic scale, extent, on an observation or measurement scale on results, which is the modifiable error unit problem, on our results. Both will be more severe when the bandwidths, the optimal bandwidths for those condition variables are smaller. Think about if the process were the same everywhere, it wouldn't matter how we dice and slice space. We'd get a similar result. But if the processes are spatially varying in a strong way, like the African American vote, for example, African American concentration on voting, when we dice and slice space differently, we're going to get different results. And that's the modifiable error unit problem. So I think that there's an in here to these problems, and also obviously the extent issue as well, in terms of thinking about local relationships. Okay? So I think there's something there, I'm not sure what. Okay, so thank you for your attention. Okay, right, thank you.
Any questions? Faith.
Regarding the statistics Fotheringham part, I should say something about, I mean, it does show processes. And we know that there are links between physical processes and variogram shapes, ranges, and so on. So also, if you superimpose different processes, you can have different breaks in the variogram. So you have a nested variogram with different ranges. So geostatistical approaches do show process level. Now, we will to see what are the links between MGWR and a local co-creaking approach, because your bandwidth essentially has something to do with the degree of dependence between two variables, the primary and the one independent. And I have a hint, a hunch, somewhere there must be a link between...
I agree with that suspicion. However, you talk about two variables, right? It's going to be hard to extend that to 14 and have
there are automatic ways to do it.
The intricacies. You're forcing it to do something it's not designed to do in a way. This is designed to, it's easy to extend this, and that's the difference. So, but I agree with you that if you had condition the semi-variograms in a manner like you're doing here, you should get something similar. Yeah, but that's what this is. This is conditioning. Yeah, in arguably an easier way. The two things are designed to do different things. It's like a Ferrari engine and something that's built on an Amtrak freight train. Right? They're designed to do different jobs. Yeah. Sorry, yes.
And is it a similar? Your method, I think, is very interesting, effective apparently. Have you compared your method with scale variance method, which was published in 1972, I think, by Mollering and Gubner?
I've seen that paper.
I thought that was a interesting approach. I always wonder why people have not picked up.
But again, I think that's more of a descriptive statistical approach. And again, the depth here, it's easy to extend this, right, to many condition variables. So you can condition it on a 14 here or 13. It's easy to extend it in this framework. And again, you're trying to force something into this particular way of doing things, which is actually easier. I'm not convinced that an alternative way of doing it would be better. But again, if you had a simple situation, then the results may be comparable. I don't know.